Rational functions and powers. This will be the third video on how to graph rational functions. By the time we finish this video, you're going to have a pretty good idea on how you can draw these graphs somewhat accurate. You're going to have a lot of details that you're going to be able to put into these graphs. Okay, the main focus is going to be on powers, when we raise things to certain powers like squared or cubed or so on. For the beginning part, I'm going to talk about a couple of really easy ideas that have nothing to do with powers, but will make the graphing go a lot easier. Okay, y-intercepts. A y-intercept of any function is where the x value is equal to 0. Okay? To find a y-intercept of a rational function, all you really need to do is plug a 0 in where you see an x. Okay, the y-intercept is when the x value is 0. So if we just plug a 0 in for the x, we can figure out what the y-intercept is, and that's a point that you can plot. All right, for the first f of x, if we were to plug in a 0 here, you would end up with, actually, let's write it like this. F of 0 is going to be equal to negative 1/3. Okay, when x is 0, the output is going to be negative 1/3, which means you have a y-intercept at negative 1/3. For the second, f of 0, let's see, if you plug zeros in, you're going to get 0 over 5, which means you get 0. In this case, the y-intercept is also the x-intercept. It's going to happen at the origin. The last, f of 0, if we were to plug zeros in here, we would get 1 over negative 1, which gives us negative 1. So you have a y-intercept at negative 1. All right, so if we can graph y-intercepts, we should consider whether or not we can graph x-intercepts. And you can do it somewhat easily in most of the different cases here. That would be assuming that you don't actually have a horizontal asymptote at the x-axis, right? Because then you might not have any x-intercepts. Okay, the opposite is how we approach this. Instead of making the x's 0 to figure out the y-intercept, what we're going to do is make the output of this equal to 0. We make y equal to 0. Then we solve for the x's that would make that happen. Okay, now as you look at the different functions here, you might say, okay, that's going to be a little bit complicated. If I were just to set this side equal to 0, then try and solve that, how do I actually deal with that? Well, the trick is you don't need to pay attention to the denominator. You don't need to look at that part. As long as the numerator becomes a 0, then you're going to get an x-intercept. With a little bit of an extra note here, that if the same value you plug into the numerator to make it 0 makes the bottom 0, then it's actually an undefined point and will probably turn out to be a hole, though it could also be an asymptote. All right, so for the first, really all you're going to do is take 2x minus 1, the numerator. You're going to set that equal to 0, and you're going to solve it, which is going to turn out to be 1/2. You have an x-intercept of 1/2. And since that value does not make the denominator 0, then that's true. It is an x-intercept at 1/2. Okay, for the next, we just take the numerator, set that equal to 0, and, well, you're done. You're going to have your x-intercept at the origin. That's where it's going to exist. Okay, now does that value make the bottom 0? It does not. It's going to leave behind a negative 2, so this is good. Okay, for the third, set the top equal to 0, solve, x is going to be negative 2. Okay? However, in this case, if you look at the bottom, that is going to factor into x plus 2, x minus 2. And if this goes here, we actually get a 0 in the denominator, which is going to make this undefined. In this actual case, what's actually going to happen, and you've seen this before, you really have, you've seen this before, the x plus 2 and the x plus 2 are going to cancel. They're going to cancel out, and you're going to be left with this part. So that means that you're going to have a hole at negative 2. Okay? The graph is going to appear to cross the x-axis at that spot, but it is actually going to be a hole. All right, we're going to go ahead and start talking about powers. Example 1. When a factor is present an even number of times in the denominator, the rational function has togetherness at a vertical asymptote. All right, let's go ahead and consider j of x. The bottom is written in standard form, but if we were to factor it, you would notice that you have a factor an even number of times. Okay, this is going to factor into x minus 3 times x minus 3. Okay, so you have a double factor. It counts twice. And because of that, you're going to get what is called togetherness at a vertical asymptote. All right, so what vertical asymptote is that? All right, remember that in the bottom, if you have a value for x that will make it 0, it's either going to be a whole or a vertical asymptote. The value that would make the denominator a 0 in this case would be a 3. Okay, now that factor isn't in the top as well. We don't have an x minus 3 in the top. So that's not going to be a whole. It is going to give you a vertical asymptote at 3. In addition to that, we could go ahead and draw a horizontal asymptote because previously we had looked at end behavior. The degree of the numerator is actually going to be 0. The degree of the denominator is going to be 2. So since you're bottom heavy, you're going to get a horizontal asymptote at the x-axis. And just previously, we had talked about intercepts. Okay, this is not going to have an x-intercept. There's not a value that you can plug into the numerator that would make this 0. Okay, so we don't have an x-intercept, which kind of makes sense because we have an asymptote here. Though sometimes you can pass the asymptote. Okay, in this case, you're not. But the y-intercept, we could think about what that is. The y-intercept is going to be the result we get by plugging 0 in for the x. Okay, so I'm going to go back to standard form. If I were to plug a 0 in for the x, this all cancels except for the 9, which means that the y-intercept is going to be at 1/9. It's going to be really close to the origin. Okay, it's going to be located about here. So what does that tell us about the graph? It tells us that we absolutely are going to have a graph over here. Okay, now as far as the rest of it, you can't have a graph underneath it because then it would fail to be a function. But we could either be here or we could be here. And remember, because we've got the double factor, we're going to get something that's called togetherness. All right, so I've got it typed in. I've got it typed in as y1, but I've got y2 turned off, which is the next function. We'll go ahead and graph. You've got that vertical asymptote at 3. The rest of the graph is over here, and this is our togetherness. Around this vertical asymptote, the graph is going to come together. Okay, as you move into that asymptote from either direction, the graph is going to come together. And that's what we call togetherness. And that's what you will get whenever you've got a double factor in the denominator. Okay, so let's take a look at k of x. You've got a double factor of x plus 4. That means that your vertical asymptote is going to be at -4. You're also going to get togetherness around that. Okay, horizontal asymptote is also going to be at the x-axis because you have degree 2 in the bottom, but you have degree 0 in the top. We don't have any x-intercepts because there isn't a value for x that you can plug into the numerator to get a 0. However, a y-intercept, if you were to plug in a 0 for x, you would get -1 over 4 squared, which would give you -1/16. So your y-intercept is super close to the origin right here. So that means that part of your graph is going to be here. And since we have togetherness, the rest of it is going to be here. The graph needs to come together at that vertical asymptote. All right, so let's take a look at that in the calculator. And you can see we've got the togetherness here. Example 2, when a factor is present an even number of times in the numerator, the rational function has tangency at that root. All right, remember that the numerator, when set equal to 0, is going to identify the roots. So we're going to get something called tangency at those roots if the factor is listed twice. Okay, so let's take a look at g of x and start by actually factoring the numerator. What multiplies to give us +4 also adds to give us -4. This is going to factor into x minus 2 times x minus 2. All right, so what we learned from that numerator is that you are definitely going to have a root at 2 because 2 is going to make the whole thing 0. So we're going to have a point here. In addition to that, let's go ahead and mark off the y-intercept if we can. Okay, if you were to plug in zeros for all the x's, you'd get 4 divided by 2, which is going to be 2. So you're also going to have a y-intercept at 2. And other things that we've picked up along the way are asymptotes. For this, we're going to have a vertical asymptote at -2, because that would make the denominator equal to 0. Okay, so we get a vertical asymptote here. We do not have a horizontal asymptote. The reason is because the degree of the numerator is greater than the degree of the denominator. However, the difference in the degrees is 1, which means that we will get a slant asymptote. Okay, so if we did a little bit of division here, we could figure out what that would look like. And for this, we could do that with synthetic division. Okay, in the box, we're going to place -2. What would be the roots? And outside the box, we're going to write our coefficients. We got 1, we've got -4, and 4. Okay, synthetic division, we'll drop the 1. 1 times -2 is -2. Actually, I got ahead of myself there. Is going to be -2, which will give you -6. And to be honest, the rest doesn't matter, but you could multiply. You're going to get, would be 12 and 16. The rest doesn't matter because that will be the remainder part. This is going to give us our slant asymptote, which will be y equals x minus 6. All right, so your y-intercept is going to be way down here at the bottom. In fact, it's going to be just off of my graph, but it is going to have a slope of up 1 over 1, which means you're going to have a point here, 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 and so on. Okay, so we have a slant asymptote. The graph is definitely going to exist over here because we have some points in that spot. So now at this point, what I'm going to do is go ahead and graph it in the calculator and see what it looks like. And in addition to the actual graph, I went ahead and added in the slant asymptote so that we could see that with it. Okay, and there is your graph. Okay, what you can't see is the vertical asymptote at -2, but that's running right along the edge over here. Okay, and tangency, that's what all this is about anyway. Tangency is going to describe when the graph bounces up against the x-axis and then turns around. So if you look real close, it's right there at 2. At that root, the graph isn't going to actually pass through it, but it's going to bump into it and change directions and match up to the other asymptote, which would be our slant asymptote. So the graph looks like this. It bounces off right here, then it's going to run along that asymptote. All right, so where is the rest of the graph? Because most of these come in multiple parts. Because of our slant asymptote, the other part of the graph is somewhat far away from it. So what I'm going to do is just go ahead and zoom out so that you can see the rest of it. And you're going to notice it down there at the bottom. Again, it does run along that slant asymptote that we see, all right? Matches up over here, matches up over there. Hard to see it, but you got your tangency over there in the middle. All right, and for h of x, we'll go ahead and factor the top like we did over here. For that, we're going to be looking at a GCF. You can factor out x squared. You can factor that out, and that'll leave you with x minus 3. Okay, then the bottom is just x minus 2. All right, in this case, things that we learn about roots. Up in the top, you're going to have a root at 0 and also at 3. You're going to have a root here. You're going to get one at 3. But at 0, because that's raised to the second power, you're going to get tangency. The graph is going to bounce against that, either this way or from the bottom side. It's going to bounce there. Where the other root, which we have over at 3, it's just going to cross through it. It's going to do that. Now, we don't know the direction yet, if it goes this way or if it goes that way, but it's going to cross through it. As far as asymptotes, you do have a vertical asymptote at 2. With regards to horizontal asymptotes, you don't have one because the degree is greater on top. In fact, the degree here is 2 degrees greater than the denominator, which means that you're also not going to get a slant asymptote. This will be a different type of picture that we see. So at this point, I've pretty much graphed everything that I know how to do thus far. So what I'm going to do is move over to the calculator and just take a look at the graph. All right, and there we go. You're going to notice that you do have the tangency here. It appears to almost be a parabola, except it's lopsided just a bit, right? It approaches this asymptote over here, and the rest of the graph comes from the bottom over here and heads off in that direction. Probably not that steep. Actually, it was more steep. For example 3, we're going to attempt to put everything together, okay? We're given a rational function with a bunch of factors in here. We're going to figure out the roots. We're going to figure out the asymptotes. We're going to figure out if it has any tangency or togetherness. We're going to figure out what the end behavior is. That would basically be your horizontal asymptotes, if you have those, or if it goes up or down. And we're going to figure out the y-intercepts, which we don't actually have to do in this order, but those are the main things that we're going to use to put the graph together. Okay, let's go ahead and just start with the roots, because those are fairly easy to work with. The roots will be the values that make the numerator equal to 0. That would be 3 and -2. However, -2, that is a double factor. So what we are going to get there is tangency. We're going to get tangency at x equal to -2. Okay, well, remember that that one is tangency. All right, so let's go ahead and plot these points before I forget. We got a point at 3, we got a point at -2. -2, you're going to have tangency. I'll put a little t there. Now, I don't know if it bounces on the top side or the bottom. Don't know that yet. But given the rest of the things that we'll discover, we can probably figure out what it's going to do. Okay, let's take care of this. Asymptotes, thinking vertical asymptotes, because E is going to be for your end behavior, which would be horizontal asymptotes. Okay, so vertical asymptotes, those are going to happen at 2 and -1. All right, so let's add those in. All right, so we actually have 2 vertical asymptotes, which is different. All right, so end behavior, let's take a look at that. This tends to be an easier thing to do if you've got it in standard form, but we actually have factored form. So what I'm going to do is imagine, if I were to multiply everything that we have in the top, what would be my leading term? In this case, it would end up being x cubed. It'd be an x cubed, because you'd have this x that gets squared, so you get an x squared times that x. The highest degree you're going to get is cubed. You can get a 3rd degree. The coefficient of it would just be a 1, because we don't have any other numbers in the front. So it's x cubed. For the bottom, if you were to multiply this out, you would get x squared, which is going to reduce to x. In this case, the degree of the numerator is greater than the degree of the denominator, which means that you're not going to get a horizontal asymptote. The degree is 1 greater, so you are going to get a slant asymptote. Okay, you are going to get a slant asymptote. Now, what I'm not going to do is go through the process of actually dividing this out to figure out what it would be, but it will be a slant asymptote. And it's going to move in this direction. It's going to move in that direction. As you plug in larger and larger positive numbers, this comes back with a larger and larger positive result. So it's going to go up to the right. Okay, the y-intercept, you're going to get that by plugging in a 0 everywhere you see an x. Okay, so if you plug in a 0 here, you get -3. See if I can fit this in here. You got -3 multiplied by 2 to the 2nd power. That's actually 4. Okay, and then underneath that, you're going to get -2 times 1. So we get -12 over -2, which is 6. So you get a y-intercept at 6. So you got one up there. All right, so the rest of this is really going to be based on like matching up puzzle pieces. We start to think about what is possible in a certain area. Once we draw that spot, we're going to make decisions about the next area around it. For example, over here, I do have a root of 3. So the graph actually has to pass through that point. It has to pass through it. In addition to that, we have an asymptote to the left. So the graph is going to need to run along that. Okay, but if our end behavior tells us that we got to go up to the right, we need to be moving in this direction as we go out. So the only way I can draw this side is to let the graph be close to the asymptote on the bottom end and head out that direction. Okay, so now that I've got that piece, I can start thinking about the other parts that we have as well. Go back to this side, okay? We've got tangency here. The graph is going to bounce against it, It's going to bounce against it. Okay, but our end behavior tells us that we have to come from this direction. So we can't be on top. We have to be on the bottom side. So it's going to look like this. It's going to bounce against, then follow that asymptote. Okay, now we got one more section that we need to draw, which is in the middle. Okay? We've got one point that's up here. The graph has to go through that point. It has to go through the 6. But along these asymptotes, we do not have togetherness. We don't have togetherness, which means that the graph can't be here and it can't be here. So the only positioning for it is going to be up top. In addition, the graph is also going to have to turn around because we don't have any roots that are here. It's impossible for the graph to come from the top, go through that point, then head down in this direction without passing through the x-axis again. Okay, now this is a rough sketch. Things aren't going to be perfect. So now what I'm going to do is go to the calculator and see how close it looks. And like before, I've already got it typed in. Okay, and we're going to hope that when I graph it, it's going to look like this. And by the way, we did not draw a slant asymptote, but we're expecting that there would be a slant asymptote. So let's hope that it ends up around here, okay, that it would have an intercept that would be above the origin. And there you go. That looks pretty good. And there's some things that are going to be a little bit different. This, I drew it a little bit more symmetric, obviously not symmetric over here. But we got our end behaviors correct. We got our asymptotes. The graph does exist up here.
Later, blah.